Okay, so this is presentation, what we're talking about. So we're talking about gas turbine performance. And well, what is this all about? Gas turbine performance is basically determined by characteristics. And you could say that a gas turbine is a system composed of components that have their individual component characteristics, and that is a very important notion for our course, because we are also doing system simulation. So if we are able to model the characteristics of the performances of the individual components and the relationships, then we have a system model and we can actually do the system simulation. So component characteristics, those are intakes, compressors, combustion chambers, turbines, etc. And they will all have, apart from performance characteristics like pressure ratios and temperatures and power output, efficiencies, they will also have limits like a stall limit for a compressor, rotational speed is limited, temperature will be limited. There may well be more limits, of course. Then we have the engine characteristics, and these are the characteristics of the whole system. Now, if we talk about engine performance, especially in operation, we talk about the gas turbine system performance parameters like thrust or power output, torque, fuel flow, specific fuel consumption. We don't look into the engine anymore. We're only concerned in the actually product of the system, and that is usually transforming energy stored in liquid fuel into mechanical power like thrust or shaft power. We can distinguish steady state characteristics and transient characteristics. So transient characteristics, accelerations of the engine, how fast is the response if you slam the throttle in an aircraft, say from idle to max. And then we also have power limitations for the whole system, also determined by the component limits, pressures, low rotor speeds, and stall. So, and these limitations that are actually coming from the component characteristics eventually mean there are limitations to the power output or the thrust output of that particular engine. So, to describe characteristics of components, we like to use dimensionless groups, because then we can actually describe the characteristics of, say, a compressor, for example, independent of the inlet conditions. For an ideal gas, the performance of a turbo machine is a function of a dimension, so D, so say diameter, rotor speed, mass flow, in and output pressure and temperature, viscosity, and ratio of specific heats. And then Buckingham, about I think 120 years ago, a scientist in the UK, I believe, devised this P theorem, say that if 3 fundamental units are present, you can reduce the number of variables that describe the performance of that system by 9 minus 3 into 6 non-dimensional groups. And the relations among those groups describe the performance consistently. Now we use 4 primary groups: pressure ratio, corrected mass flow, and well, we'll get into that. And 2 groups are often ignored for gas turbines. So what I'm saying here, a turbo machine, theoretically, well, the performance is a relationship among 9 parameters, and then we can reduce that using the pi theorem to 6 non-dimensional groups, which is then an efficient way to describe the performance. These 6 non-dimensional groups are then 4 primary groups and 2 groups that we often ignore because they don't have a big effect. And those are viscosity, which have a marginal effect, which affects Reynolds, and it has a marginal effect on efficiency, only for well, particularly aero engines, what we're talking about, we take this effect into account because at high altitude the Reynolds number is substantially different from sea level, and then it has a small effect but a significant effect on the efficiency. And gamma, ratio of specific heats, we only use if we are assessing the application of a turbo machine for different media. It has, of course, a very small effect also if we're just looking at air, because of the small change of gamma, but it's usually, we can usually consider it negligible, also in relation to the uncertainties and the error margins we have, which are then larger. So if we have very large temperature changes, then or different media, then gamma will change substantially, and then we have to take that into account. So for aero engines, it's usually only the first one that we take into account. Now, the primary groups are a group for mass flow. So we can mass flow fully dimensional by the term on the top left. So mass flow times the square root of the gas constant times the total inlet temperature over diameter squared and times the total pressure, inlet pressure. But then if you take out the constant factors like R and D squared, and you divide the temperature and the pressure by the standard temperature and the pressure, you get a very convenient corrected mass flow number, as we call it, a parameter, which is mass flow times square root theta over delta. And theta is the ratio of the inlet temperature over the standard temperature to the standard temperature, and then delta is the inlet pressure over the standard pressure. And the nice thing about using this corrected mass flow, which is not fully, well, not dimensionless anymore, but it's still able to represent the mass flow or the flow condition in the turbo machine, and independent of the inlet conditions. So basically, it's representing the actual flow Mach number. The nice thing about it is if we are operating around standard conditions, so standard pressure and temperature, then that corrected mass flow is the same as the real mass flow. So you're actually working with a parameter that is in the order of magnitude of the real, the actual mass flow really in kilograms per second, for example. And that is convenient, so then you know where you are, so to speak. And if you don't do that, if you would just leave, if you would not use theta, but instead use the temperature, and instead of delta, you would use the pressure only, you would get your corrected mass flow parameter would have a completely different order of magnitude than the actual mass flow. Now, the second group is pressure ratio, total ratio of exit pressure over total inlet pressure. You can also do it the other way around. It doesn't make a difference. It's already dimensionless, so we don't need to worry about that. And then we have rotor speed. And the full dimensional form is then rotor speed times the diameter, which is the velocity, over the square root of RT, which is also a dimension of velocity. And if we then just leave out the R, which is basically constant, or almost constant in most cases, for most cases, we have rotor speed n over square root theta. If we divide the temperature over the standard temperature, and then we also have a very convenient corrected parameter for rotor speed in the same order of magnitude as the actual rotor speed. Now that corrected rotor speed is proportional to the Mach number of the blade in the circumferential direction. You could say the blade tip, but it doesn't matter. It's proportional to Mach. So these two numbers are very much in, well, in terms of aerodynamic properties. Sometimes when you, as a gas turbine system engineer, talk to people who do CFD with compressors, you have to explain this, because they don't understand that we use these, what these numbers are. But if you say them and they don't understand how we can actually represent performance of that compressor, but in their terms, if you would explain that the corrected mass flow is actually the actual Mach number and the rotor speed parameter is actually the blade Mach number, then you actually talk the same language again. Then we have the efficiency, which can be isentropic or polytropic, and that is derived from the ratio of the outlet temperature over the inlet temperature. So, well, these are the four-dimensional, four primary groups to describe performance of a compressor, turbine, or a fan. And then we have the extra group, which is the Reynolds effect, which is actually represented dimensionless parameter describing the effect, describing the viscosity in a non-dimensional sense, and it has an effect on efficiency. So usually at high altitude, you say that with the drop in Reynolds number, there's some sort of you have some sort of simple function that means that a drop in Reynolds means a small drop in efficiency. It's a usually a very simple relationship that is used to predict performance of aircraft flying at high altitude. Yeah, you see an example of a plot where that is analyzed here. Okay, so when we're not talking about the ratio of specific heat gamma, because that is not really used in normally not used for analysis of aero engine performance. Okay, compressor characteristics. Well, you should be familiar with this. We have this chart represents the relationship among the four primary parameters. So we have pressure ratio versus corrected mass flow, and for a number of constant values of corrected rotor speeds, which are the solid lines from bottom left to top right. And then you see the dashed curves, which are curves of constant efficiency. And we also see, and now we're going to the system already, we see the equilibrium running line. Now typically a compressor in a gas turbine, when the compressor operates in a gas turbine system, then the operating point of that compressor stays at a single equilibrium running line, especially in the higher power region. So near point A, regardless of what you do, of inlet temperature, etc., you always stay on that line, that dashed line that is going from bottom left to top right. At the lower region, it may change a little bit, but at steady state, you're basically on the same, you stay on the same line, unless the condition of the compressor changes or other component characteristics change somehow. So, for example, due to deterioration or corrosion in either the compressor, or can also be the downstream turbine. The location of that operating line is determined by the compressor itself, but also by the cross-sectional areas downstream the compressor. Now, if we accelerate, we will usually go higher than the equilibrium running line. If we decelerate, we go below, but that comes later. Any questions so far? Okay, well, this should also all be familiar, of course. So for a turbine, we have also characteristics, but we have a different way of describing the relationship among the four dimensionless groups. We cannot usually, it's not very useful to try to do it in a single chart. So we usually take first the bottom one, which is also corrected mass flow against pressure ratio. So that's actually the inverse as we do with the compressor. And then we see that the corrected mass flow eventually stays constant in the choking region. That is, if the pressure ratio exceeds beyond a value where actually the passages in the turbine nozzles, or maybe even for status nozzles, or even the rotor blades, between the rotor blades, the flow starts to choke, and then the corrected mass flow cannot increase anymore. Below that point, it's depending a little bit on rotor speed. Beyond that point, it can also be depend a little bit on rotor speed, especially if it's a multi-stage turbine. Well, there's a lot of theory you can look up in literature here, but this is basically what it looks like. So, and it makes actually a number of things easier, and you can make interesting shortcuts if you want to manually calculate or predict off-design performance in a gas turbine, because if it is in the high power region, usually a turbine, especially the high pressure turbine, is choked, and then you can actually assume that the corrected mass flow is constant. Also, if you change other parameters, because it is somewhere on that horizontal line to the right where choking occurs. Now, the efficiency of the turbine is then also plotted, and there's various ways to do it. And here we plot it as a function of pressure ratio for different corrected mass flow of corrected rotor speed values. And you see different extremes, and basically it is that the lower rotor speeds, the lower rotor speed values have their maximum efficiency at low pressure ratios, and the higher at high pressure ratios. So for good efficiency of a turbine, you could say that at low pressure ratio, you want to stay at low speed. If you go to higher pressure ratios, you go to high speed. You can actually make interesting analysis why that is, but that is beyond the scope of this lecture. So that's the turbine. Then we have the inlet. So the press compressor and turbine, of course, are the turbo machinery components, which are more complex. And just to go back a little bit, we here have the representation using the 4 non-dimensional groups, or the 4 groups of the 4 corrected parameters: corrected rotor speed, corrected mass flow, pressure ratio, and efficiency. If we would here also involve Reynolds for high altitude, it would actually only mean that there's a delta on the values of these efficiency curves here, depending on the Reynolds number, which is and the Reynolds number you can actually almost make a consistent function with altitude. Okay, so now we go to simpler components like the inlet, which is actually basically a pressure loss function. That's what you get from the inlet in terms of system simulation. Of course, if you go to more detailed multidimensional simulation, you're talking about flow distortion and stall, and gets a lot more complicated. But for the system performance, it's actually only the pressure loss that you're interested in. And the pressure loss is depending on usually the flow rate, and then it's best to use the corrected mass flow rate. And then for aircraft, also the Mach number. And you can actually even use some other parameters. It's very often an empirical relationship that is established by CFD simulations or measurements. For civil turbofans, the RAM recovery, which is basically the 1 minus the loss, so it's basically the efficiency of the inlet, is at least 95%. But for military engines, where you want to fly much faster, it is different. They are also optimized for high velocity. So this is, for example, is the F-16 inlet that you see here. And it has its maximum inlet efficiency at about Mach 0.8, and that is the design point. The F-16, so a civil turbofan engine, as it's running at max power at takeoff, and then of course, and then also at cruise, you want a high inlet efficiency because of fuel efficiency. But also at takeoff, you want a high fuel efficiency because of the requirement for thrust. So you need both. And so you have a very round inlet lip, which nicely guides the flow into the engine, and that works so well between Mach 0, so no velocity at all at the start on the runway, to cruise power. Now, an F-16 is designed for Mach 0.8, so in that respect, it could, if you would not want to fly any faster than Mach 0.8 with an F-16, you could do the same, and you would have an almost flat efficiency here. But you also want to use the F-16 supersonically, and then you need a very sharp inlet lip. And that if you imagine, or if you remember what the F-16 looks like, with a big inlet under its fuselage, about somewhere below the cockpit, with a sharp inlet lip, that is to maintain a decent, some reasonable efficiency at supersonic speeds in terms of the supersonic aerodynamics there. But a sharp inlet lip is not very efficient if you at standstill. And it's probably also smaller, so the cross area of the inlet is reduced to also allow supersonic efficiency. If you would make it as big as we'll use the same design rules as for a civil subsonic turbofan engine, it would not work at all supersonically. So that actually means that the engine at standstill, at takeoff, has to actively suck hard. Suck in the outside air, and it also has to, and the flow is not very well guided because it has to go in over a very sharp inlet lip, and that causes a loss. So that means that at takeoff, there's about a 15% pressure loss. So there's this line here, pressure loss in that inlet for the F-16. Now that's not a big problem because for a military fighter, takeoff power thrust is not really an issue. I mean, even if you have a short runway or you load the fighter with a lot of stores or payload, you can always use the afterburner and then you will always have, in most cases, have way enough thrust to complete that takeoff. And there's a small penalty of that afterburner in terms of fuel consumption. Such a short period is actually small. So it's actually because of the design requirements for a military engine to have very high thrust at higher altitude also that this is. So that's a lot different. We're looking at civil turbofan engine. It's much simpler. You can for a first order estimate, for example, of performance, many people just assume that the ram recovery is 1, so there's no inlet loss at all. But of course, it is an issue. So here you see crosswind. This is an old chart. So with crosswind, the inlet has to guide the flow. If this is almost like as sharp as an F-16 engine, you would have a substantial loss here already. But if you would have a modern big turbofan engine with a much larger diameter, the inlet lip would be the inlet lip diameter, the radius of the band would be much larger. And even with crosswind, there would be no flow distortion. But in this case, you would have a boundary layer breakup here. And actually, the compressor doesn't like that. But then again, you get into the aerodynamics of the compressor itself, which is a different topic, but one thing, it will cause stall. So this is another chart on inlet efficiency. It's actually the same. So at cruise it's 0.98 inlet efficiency, but at takeoff the F6 inlet ram recovery is 0.89. So okay, 11% loss, which is actually quite dramatic. Then we go to the exhaust nozzle. Are there any questions, by the way? No, then we go to the exhaust nozzle. So the exhaust nozzle is to establish expansion of the gas, to conversion of potential energy, which is high pressure, and downstream the last turbine into kinetic energy, which is high velocity. You can have both a subsonic and supersonic exhaust nozzle. So again, military engines will be able to have a very high pressure ratio across that nozzle. So they will actually, the exhaust nozzle will accommodate expansion to supersonic velocity. The geometry is very important. Military engines then often have variable geometry, losses, shock waves. We can have for a civil turbofan a cold or a hot exhaust, but they can also be mixed. And then here, and excuse me, it's barely readable, but we can also have thrust reversing, and that is to reverse the thrust in a sort of almost forward way. So we actually turn the thrust factor forward, not entirely forward, but sort of slanted to have a brake effect during the landing. So in exhaust nozzles, in terms of characteristics, we also have a small pressure loss. That's of course minimized, but this is also something in the order of 5%. It's maybe a bit more sometimes. An exhaust nozzle is also a small hole with, well, actually a vessel with a, you can actually compare the exhaust nozzle with a small hole in a big vessel through which gas escapes. And then again, the same happens as a turbine. And the characteristics of that exhaust nozzle is then similar in that the corrected mass flow will increase up to a point where the Mach number becomes 1 in the throat of that nozzle. Will be around, pressure ratio will be around 1.9, and then choking occurs and the corrected mass flow will not increase anymore. The velocity may increase downstream the nozzle if there's a divergent part in supersonic expansion, but the corrected mass flow, which is the mass flow times square root theta over delta of the inlet, as for the inlet conditions, will not change anymore, even if the supersonic expansion. So in engineering practice, we do not use isentropic efficiency. We can. I will show that. No, I don't have that, but you can actually. Yeah, you can apply, you can work with an isentropic efficiency number that will come back later, but that is for very theoretical cases. But in engineering practice, as with the inlet, actually, we describe the efficiency in terms of a pressure loss or pressure losses, and also and these actually translate in a velocity coefficient. So if we expand the gas in the nozzle, we could ideally expand up to a particular velocity if you would calculate without losses. But if then in reality you will have a velocity Cj, that velocity will be a little bit lower. And you can imagine that is because of boundary layer friction effects, other effects, pressure losses, because it always coming, well, you can relate it to pressure losses, and then you lose 2 to 3%, as you can see. You also have the discharge coefficient, which actually means that the effective flow cross area is a little bit smaller than the geometrical area, and it's basically the boundary layer that sits in between. So the gas simply cannot have the velocity, the same velocity as in the center of that nozzle at the walls because of friction. And then we talk of an effective area, and the ratio of effective over geometrical area is the discharge coefficient. And then we can also use the thrust coefficient, which is a more direct factor of the thrust versus the ideal thrust that we could obtain if we would have ideal jet velocity, but then actually Cx and Cv represent the same loss. So very often only only one of CV and CX. We either use CV or we use CX. That's basically what often used. So that basically CD and CV, or we use CD and CX as parameters to represent the efficiencies in the nozzle. Now these values are here constants, but in reality and in detailed models, we actually establish functions of those factors, functions of typically corrected inlet mass flow. And sometimes even other factors also, if the nozzle is variable, then also the geometrical nozzle area will be a parameter in that function. But for more simpler simulations around single operating points, we just use single constant numbers, constant values. And also these relationships and these values are established by either CFD and especially in the past by tests. So it's not, you cannot use a direct thermodynamic analytical derivation for it. It's empirical. So critical pressure ratio. So this is again, and it's not, I'm not sure, but this is to explain how the propelling nozzle really works and how the gas, the thermodynamics around it work. And it's not very extensively explained in the Aero Engine Technology course, as far as I remember. It never was really. But suppose we have a vessel, a reservoir, and we have a pressure in that reservoir, and which is the green area here, and we have a lower pressure outside, the ambient pressure, and we have a small hole here, and it's already shaped like a nozzle, as you can see. And you would decrease the, you would increase the reservoir pressure. Then you would have an increase in mass flow, which would eventually go this way, the dashed line. If you instead would actually keep the reservoir pressure constant and reduce the ambient pressure, then the line is going this way, and you have, when choking occurs at the critical pressure ratio, it would remain constant. And of course, if you, the reservoir pressure is constant, if we would instead of mass flow use corrected mass flow, we actually correct for the change in the inlet pressure. And then also we have this characteristic. So as we said here already, if we use corrected mass flow, we see this as a characteristic. But you can easily, well, you can do this in a test rig if you want to, for example, test the characteristics of a particular nozzle geometry and analyze the nozzles, the losses. So. And this is then how you calculate these things. So you can, we have an expression for mass flow here, pressure, and velocity, which is Mach number times sonic velocity. And then here we have a ratio between total and static properties for ice, if it's isentropic. And then eventually you can actually calculate the area that you would need to expand a mass flow W here for a Mach number M. And then you get this relationship. So if you invert this relationship and you increase the Mach number through the through that duct, then you get eventually this chart, and then you can see that if this is the throat, this is actually the nozzle shape. So this is the narrowest thing. So here the nozzle starts. So this is A. We calculate A using this relationship. And then this is the velocity. This is sonic velocity. The Mach number here is 1. And here it increases because we have a we assume that there will be no shocks and that the velocity there will be no non-isentropic phenomena. So the velocity will, the flow will continue to expand and accelerate, and from here we have supersonic velocity, and we have a Mach number that is going beyond 1 here, and the pressure ratio is also increasing, and this will then be critical pressure ratio. So these are the trends, and of course density will decrease because we are expanding. Now here you can apply these relationships, but then include an efficiency number, which is actually derived from a ratio of the temperatures, because there will be some losses. I will not go into detail here, but you can derive relationships, including an expression for the isentropic efficiency or polytropic efficiency here, and then the critical pressure ratio can be calculated using this expression. And of course, this is, well, I don't see the critical pressure ratio here, but that must be something, well, yeah, that's actually this one. Complete expansion is, this is a calculation recipe for an unchoked nozzle. This was used for the same, for when module 10A was still a separate course. You had to then manually calculate through a cycle, including the expansion in the nozzle. And here you can see that you do complete expansion, and it means that the pressure ratio is subcritical, and you can just calculate the velocity by calculating the change in temperature here, and that change in temperature here times the specific heat times 2 square root is the velocity. And that is of course because velocity squared is proportional to the drop in enthalpy, and enthalpy is a change in enthalpy is Cp times a change in total temperature. Or no, I'm not saying total in temperature. Yeah, and then you can calculate the thrust from the well-known thrust equation, for example, in this case. And here you would have, you can apply, if you want, the nozzle efficiency, which in more, well, in standard cases we assume 1, and then instead we use the discharge or velocity or thrust coefficients to represent the loss, and we're usually not using this eta for the jet, for the nozzle efficiency, so we can leave that 1. We're not going to use these in the course or anywhere in the assignments, but these equations are used, well, in a more complicated way, even because we have in GSP and in the other cycle model, but then also using relationships for how all these properties, like for example, Cp is depending on temperature and also composition of the gas. These are all small effects, but it makes it much more accurate. But if you would do it manually, you would do it like this, but it's similar. So for incomplete combustion expansion, you assume that the pressure ratio is supercritical, and you calculate the critical pressure ratio like this, and then you assume it's supercritical, and then you can say, okay, so the temperature, the critical temperature ratio is this one, and then you can, because you assume it's supercritical, you can calculate the jet velocity in the throat as sonic, which is the sonic speed here, and you can calculate the area here, and then here you can calculate the thrust, and because it's supersonic, there's some residual pressure to be expanded downstream the throat, and you have this term which you also remember from aero engine technology. You can also instead talk of an efficient and an effective jet velocity, which would then be something similar as the eventual velocity of the gas after some part of some partial supersonic expansion. Okay, so then we have convergent versus convergent divergent nozzles, so they have a different in design thrust and nozzle press ratio. Civil turbofan engines only have convergent nozzles. They don't have a divergent part, and that is because their pressure ratios are at most a little bit supercritical. For example, at cruise. So they don't actually, there's no point in adding a divergent part to the nozzles of a civil turbofan, because there's hardly any pressure ratio or pressure left to guide supersonic expansion. Although you may see in cruise a little bit of supersonic expansion, and you can even see shock waves if you use techniques to visualize that. However, for military engines, you may have pressure ratios in the nozzle that go towards 3 or 4 even, and then there's a lot of supersonic expansion, and that is then guided by a divergent part. So there's a convergent part and then the divergent part. So you could say that, well, this is of course a very weird shape, but this convergent trend here is what is used in a civil turbofan engine, but then an F-16 engine, for example, would do this, and then also there would be a structure in this sort of shape with a divergent end, and that end is then also variable, and also the throat area is variable. So there's several aspects to to actually applying a convergent diverging nozzle or a Con-D nozzle, and that is the off-design performance is different. The relation between thrust and drag becomes different because the divergent part will also have well, that represents some aircraft drag. It will mean additional weight and length. So it's also a design choice to choose a Con-D nozzle. There are also military engines like the early French engines who have no diverging part. Because if you don't apply a divergent part in the nozzle, you still have supersonic expansion. The thing is, it probably happens with lower efficiency and more losses. So it's not like if you don't have a divergent part that there is no supersonic expansion. There is, but there are cases like in the F-16 design case, for example, the designers have chosen to add additional weight and structure and spend money and costs to guide the supersonic expansion downstream the throat. Okay, so then if you look at T-Jet turbine performance simulation in GSP, and you can simply do that yourself with a T-Jet demo model, and you look at the some parameters at the end of the engine if you increase the fuel flow, and you look here at the static pressure ratio in the exit, then here you can see that at some point the static pressure ratio here increases, and this is actually where choking occurs in the nozzle. And this is the Mach number of the exit of the throat, and this is 1 here. So you can see that in the low power region of the turbojet engine, the nozzle is not choked, and that's because all the pressures and levels of course, in the engine are much lower. And here you can see that the pressure ratio of that nozzle, oh no, this is the pressure ratio of the turbine, is also staying the same. Okay, so this is actually the nozzle, and these parameters are for the turbine. So this is the pressure ratio over the turbine, which is this is an old chart, which is component 5, and this is the corrected mass flow of the turbine. This is the Mach number in the throat, downstream the turbine, and this is the static pressure in the throat. And then you can see here, if we first look at the nozzle, that at this point the nozzle will choke. Now, an interesting effect is that if the nozzle or a turbine, anything, if the flow is choked downstream a turbine, then that turbine will start to operate in a fixed operating point. I'm not sure if, we don't have that, it's in another lecture, but if you can read that also in Cohen and Rogers, and that's also a shortcut that you can use to, if you do a manual of design calculation. So for example, if you want to predict performance in the higher power region, and then you assume that the nozzle is choked, and then as soon as you assume that the nozzle is choked in this region, then you can argue that the corrected mass flow of the turbine and the pressure ratio of the turbine is constant, even if you change fuel flow here. And that is because the nozzle, as long as the nozzle downstream that turbine is choked, the turbine upstream the nozzle will operate in a fixed operating point in its map. It's actually, the reason is actually because you can describe the turbine map as a function of, as you can describe the characteristic of the turbine map using the inlet corrected mass flow, but you can also use the outlet exit corrected mass flow. And we know if the nozzle is choked, the nozzle inlet corrected mass flow is constant. We've seen that in this slide. This one is constant, but this is also the exit corrected mass flow of the turbine. And if the exit corrected mass flow of the turbine is constant, then the operating point is constant, and also the inlet corrected mass flow is constant. So it's a very convenient coincidence, but it's all for manual calculations. And in GSP, the GSP doesn't use that shortcut because there's still small variations, as you can see, because of all sorts of secondary effects. But GSP demonstrates that indeed you can do that. Of course, if you do that calculation and you arrive at some system performance condition, you need to check afterwards whether the point where you actually arrived at was indeed choked. So was your nozzle indeed choked? Because you may vary all these parameters as you are converging to your solution. Well, compressor stall, I will not go too much into compressor stall because this has been at Aero Engine Technology, but well, it's basically stall of the rotor blades. Usually incidence angle becomes too steep and you get breakdown of the boundary layer, and we have rotating stall, where actually one stall cell there's only stall in a part of the rotor and the stall cell is covering a number of passages, but it's traveling in the opposite direction of rotation of that rotor, and may cause funny effects. Stall is a problem that is not as problematic anymore as it was in the past, about 30 or 40 years ago, with civil turbofan engine operation. Here you see the compressor map again. Oh yeah, here you see stall at low rotor speeds. This is important. If you, and usually I do a drawing on the blackboard here, but I cannot do that now. But you must imagine that the compressor is designed for a specific design point, which means which is a particular pressure ratio. Now, if you operate that compressor at a much lower pressure ratio and rotor speed, the convergent passage of that compressor is not suitable anymore. Actually, the compressor final stages expect actually the air in the design point at a very high density, but at lower power it doesn't have that density anymore. So actually it's too small, and as the end of the compressor is too narrow, there's a sort of blockage, and as a result it will try to speed up there, and the speed in the first stages of the compressor, so I'm talking about a multi-stage compressor with say 10 stages, so the speed in the first stages of that compressor will be relatively low, and that will have an effect on the velocity triangles. So this is 0.3, which is low speed, and then here you can see that 3 in the final stages it will, I don't see 3 here, do I? Yeah, in the final stages it will be very high, but in the first stage it will be very low. And then here you see what happens. So the yeah, this is the absolute velocity in the axial direction. This is the rotor. This is the direction of rotation, and this is the relative velocity relative to the blade, which determines the incidence angle, the angle of attack of the blade. So if this angle becomes too large, we get stall. Now, if we go to a low rotor speed and low pressure ratio operating point, which is actually here on the operating line, and I already explained that in a jet engine or in an aero engine, steady state, the operating point will always be on this line. It will not go up or down unless we are in an acceleration or deceleration, but in steady state it will be here. Then the axial velocity will drop substantially because also the flow rate will go down, because here we're going to the left if we are at 3. So this is 0.3 in that characteristic. And then of course also the rotor speed will drop, but the drop in axial velocity is stronger, meaning that this relative velocity factor will turn to this red one, which means an increase in the angle of attack here. And if we continue, then eventually we get to some point where we get stall. So the problem is that if we go to low power, the drop in axial velocity in the first stages is more than the drop in rotor speed or the drop in the velocity, circumferential velocity of the vanes of the rotor blades. Sorry, I should say rotor blades. And very often, a lot of system simulation puzzles are focused around this problem, because there's various ways you can actually change this. You can change the stator vanes or inlet guide vanes, or you can actually control this factor if you like. But then you have the variable geometry case. Now we're going to that solution now. So if we have variable bleed valves, that's the first. This is another one, variable bleed valves. Then we can actually increase this velocity again by blowing off air at the end of the compressor or halfway the compressor. So if we are here and we say now we want to increase this velocity, and that actually we open a valve halfway the compressor, and that means that the velocity in the first stages of the compressor will increase again. The problem is we waste energy, so we do this with startup only, and these are the big valve sort of things that you see around the compressor casing if you look at an engine that is uninstalled. It's only at startup today, because then it doesn't matter that you're actually wasting energy. There's only one engine that also uses it during operation, as I know, and that's the J85. That's actually the T-Jet demo model in GSP. And you can actually simulate this opening of the valve by letting off bleed halfway the compressor and then see that indeed the compressor will not exceed the stall line here, because if you now run the T-Jet simulation to partial power, you will cross the stall line. You will, if you do the quick start basics in GSP. So this is one way to fix the problem, but it's not very efficient, and so you can only use at startup. This is another one. You can say, well, I just divide the compressor in smaller compressors with fewer stages, and that also reduces the problem, because if this problem is particularly severe if you have many stages when you have a large variation in flow cross area through that compressor and they're all running the same speed. So this is a solution that Rolls-Royce applied. Rolls-Royce has a triple spool engine, so that is for a part solving this problem.